Okay, let's be real for a second. Every time an artificial intelligence writes a beautiful poem or generates one of those crazy photorealistic images, it's not actually thinking. It's really not. What it's actually doing is performing billions of spatial geometric calculations. Underneath the hood of modern AI is this absolutely beautiful kind of visual math. And today in this explainer, we are going to completely demystify it for you. Now, if you took high school math, you probably picture a matrix as just a boring grid of numbers, right? Well, we need to shatter that preconceived notion right now. As the brilliant folks over at Hugging Face put it, a matrix is a transformation from one space to another, not a grid of numbers. It is literally a machine that takes vectors from one space and physically moves them to another. Okay, let's dive into this a bit more. A static Excel-style grid, that is just potential energy. Matrices are actually made for multiplication. The very moment you multiply a matrix by a vector, it becomes a dynamic machine. The transformation is realized. You're essentially taking a point in one dimension and asking it, hey, where exactly does this land in a totally new space? So that naturally leads us to a pretty massive question. What does all this geometry actually have to do with artificial intelligence? I mean, how do we get from moving abstract shapes around in space to a language model that can write complex code, or an AI that can instantly recognize a cat in a photo? Part 1, Transforming Space and Shapes. To answer that massive question, we first need to define our core concepts. According to the researchers at Labelbox, we really just need to think about two basic building blocks. First up is a vector. Just think of a vector as an arrow in space with a specific direction and length, kind of like a set of GPS coordinates. The second concept is a linear map. A linear map is simply the mathematical process of moving that arrow. And here is the secret to the whole shebang. A matrix is simply the mathematical representation of these linear maps. If you're a visual learner, it helps to picture exactly how these linear maps manipulate physical space. By multiplying a vector by certain matrices, you can perform a rotation, literally spinning that arrow around. You can do scaling, which stretches or shrinks the space. You can do a reflection, flipping the space just like a mirror, or shearing, which kind of pushes the space sideways. AI is essentially taking complex data, mapping it out as vectors, and then using matrices to perform massive, mind-boggling combinations of these spatial transformations. Moving on to part 2, math in simple terms. But how exactly do these matrices multiply together to actually make that happen? Well, the fundamental building block of all AI math is an operation called the dot product. It's incredibly simple in concept. You just multiply the corresponding elements of two sequences and then add up the results. Geometrically speaking, as noted by the tensor tonic platform, a dot product essentially measures the alignment between two sets of numbers. High alignment means a large resulting value. Let's look at a dead simple numerical example from Giles' machine learning blog to really anchor this. Imagine we have vector 1, which is 2, 3, 4, and vector 2, which is 1, 0, 2. To get the dot product, we just multiply the corresponding pairs and add them up. 2 times 1 is 2. 3 times 0 is 0. 4 times 2 is 8. Add those together. 2 plus 0 plus 8 equals 10. That's literally it. That simple multiply and add operation is the heartbeat of deep learning. Now, matrix multiplication is really just doing that dot product operation many, many times over. The engineering team at PyTorch visualizes this beautifully as a 3D operation. First, you project your two matrices into the interior of a 3D cube. Second, you multiply the pairs of values at every single intersection, which forms this vast grid of products. And third, you sum those products along the third dimension to produce your final result matrix. So it's basically millions of simple dot products happening simultaneously, weaving all this data together.
Which brings us to part 3, the engine of AI.
And this brilliantly illustrates how neural networks actually utilize this exact mechanism. When data passes through an AI, those inputs, which are vectors representing your data, are multiplied against a matrix of weights, and those weights represent the AI's learned connections. Based on the layout from Sebastian Roschka, you can visualize how the rows of the first matrix seamlessly align with the callings of the second matrix to compute the output. So the crucial point is that the entire system boils down to this magic formula. Z equals W times X. W is your weights matrix, X is your inputs matrix, and Z is your output. By using matrices, we don't have to calculate every single artificial neuron one by one. Multiplying the weights matrix by the inputs calculates the entire layer's outputs in a single, perfectly synchronized mathematical step. It is absolutely elegant. But wait a second. An AI model like ChatGPT doesn't just have a few neurons, and it certainly doesn't just look at one piece of data at a time. So, what happens when we add thousands of neurons or need to process massive batches of data simultaneously? Well, the beautiful thing is we don't change the math at all. We literally just build a bigger spreadsheet. If we want more neurons, we just add rows to our weight matrix. If we want to process a batch of thousands of images all at once, we just add columns to our input matrix. Matrix multiplication natively handles massive amounts of parallel calculations, which is exactly why graphics processing units, or GPUs, are so perfect for AI. They're hardware optimized from the ground up to do this exact thing. Let's look at the physical limits of this in part 4, scaling the computation. Because there is a massive catch. As we push towards artificial general intelligence, our matrices are getting incredibly, ridiculously massive. An 8x increase represents a terrifying bottleneck in AI development. As the tensor-tonic analysis explains, naive matrix multiplication has a cubic cost. That means if you decide to simply double the width of a neural network layer, the compute required doesn't just double. It increases by 2 to the power of 3. Think of a 3D cube of blocks. If you make it twice as wide, twice as tall, and twice as deep, you suddenly need 8 times as many blocks. That 8x cubic scaling makes training massive AI models breathtakingly expensive. Now, what's really interesting about this is how researchers are fighting back against this cost. They are literally training neural networks to discover faster math. By representing mathematical operations as complex tensor networks, AI can actually find valid mathematical shortcuts, like Strawson's algorithm. These learned algorithms reduce the number of individual multiplications required, totally bypassing that cubic bottleneck. Let's move on and see how this builds, because even with clever algorithmic shortcuts, a single GPU chip simply isn't enough anymore. Today's AI models have weight matrices holding hundreds of billions of parameters. They literally cannot fit on a single machine. So engineers use what's called distributed matrix multiplication. They mathematically slice these massive matrices into smaller blocks and distribute them across thousands of GPUs, working perfectly in tandem. We've covered a ton of ground in this explainer today, from simple arrows moving in space all the way to the massive distributed GPU clusters powering the AI revolution. But I want to leave you with a thought to ponder. If matrices are fundamentally machines that transform data from one spatial dimension to another, and modern AI involves passing human language and imagery through billions of these geometric transformations, what unseen dimensions of meaning and logic is deep learning mapping out right now? Think about that the next time you type a prompt. Thanks for joining me, and keep questioning the data.